Section 3.2, Part 2. So we left off kind of abruptly in that last video. I saw that I was running out of time there, but we left off with this addition rule for the OR probabilities. And, you know, if there's A and B or just any events and you are maybe having not mutually exclusive, probability of A or B will be the probability A plus probability B minus the probability of the common outcomes, the things that are common to A and B. So again, up above, that would be that 3 outcome that was common, both odd and 3. So if they are mutually exclusive, and you identify that, which you always need to think about this before you really start setting things up, if they are mutually exclusive, then the common outcomes, there are none, which means that that probability of A and B is 0. So then you can just add those probabilities together without having to do a subtraction. There is no double counting, so to speak. And keep in mind, the probability of A and B that we're seeing here in this OR addition rule does not have independent events. They're not independent of each other. They have things that are affecting each other. You know, the odd, if you know it's odd, then you also have a 3 there. So that's not independent. So it must be computed differently than what we did for the multiplication rule. You can't just multiply the probability A and probability of B together to get that probability of A and B in this case, because the A and B are not independent here. There's some tie together between them. So let's put this together in an example, more like what you might be seeing. You pick one card from a deck of 52 cards. Let's give the probability of the following events as a fraction. So we're going to pick a card that is a king or an ace. So I'm just going to write this out as king or ace, using the K or A. And now I need to think, king, ace, are those two cards mutually exclusive? Well, if I draw one card out of a deck of cards, it's either going to be a king or it's going to be an ace. There's no king ace card in the deck of cards. Sometimes I wish there was when playing poker, but there is no king ace card. It's just the king or it's the ace. So we only need to add the two probabilities together because they are mutually exclusive and not have to worry about subtracting. So there were 4 kings out of a deck of 52, probability 4 over 52, same thing for the ace, and you get 8 out of 52, or reduce down 2 over 13 in fraction form for that probability. Now the next one, picking a card that is black or a face card. So in that deck of cards, you've got 26 black cards, you've got 12 face cards. However, there are 6 cards, half of the face cards are also clubs or spades, black cards. So black cards, face cards in a deck of cards are not mutually exclusive. There are common outcomes to both the black card outcome, or event I should say, and face card event. So let's go ahead and write this out then with that understanding in play. So if we want the probability of black or face, we're going to start just like we did up above by just adding the two together, but knowing that these are not mutually exclusive, that there are common outcomes, we need to subtract away the probability of any of these cards being black cards and face cards at the same time. And there are, you know, all the face cards that are spades and clubs fit into this category. So what we get here then is 26 black cards out of 52, so that's probability there, plus 12 out of 52, the probability of your face cards, and then minus, there are half of the face cards are red, half of them are black. So 6 of them are red, 6 are black, and that 6 black cards that are face cards fit into that probability of black and face at the same time. So we would subtract away 6 out of 52 to undo the double counting that happened when we put together the black cards and put together the face cards in the first 2 probabilities. So what you get here is 32 out of 52, and then you reduce this down to 8 over 13. So again, keep in mind, there are face cards that are black. So not mutually exclusive, must subtract. Just want to make sure that you're thinking about this. Where you have to subtract that probability of A and B as in the form. In this case, it was black and face. Okay, so we've looked at the and probabilities, looked at the or probabilities. With the and, you're just looking at the scenario, are they independent? If they are independent, you can just multiply them together. With the or, you're asking yourself, are they mutually exclusive, not mutually exclusive? If they are mutually exclusive, you just add the probabilities. If they are not mutually exclusive, you still can add the probabilities, but then you have to subtract away the probability of those common outcomes that we're getting double counted. So let's take a look at this concept in a two-way table, kind of brought into this new way of looking at the information. And basically common ways of organizing data, there's a lot of them out there. One of them is the two-way table. And the two-way table, basically you've got a row here that has some information, you got a column here that has some information, and then you have numbers that indicate that in this particular table there's age over 35, likes mild sauce, there's 22 of those. Likes hot sauce and is over 35, there's 17 of those. Less than or equal to 35 years of age, likes mild sauce, there's 12 of those. Less than or equal to 35 years age, and likes hot sauce, there's 28 of those. So with these two-way tables, you can easily kind of break things down a bit and look at these little individual categories that are overlaps or intersections of two different qualities. You can also just total up the column and get, in this case, the total number of people that liked mild sauce, or the total number of people in this study that liked hot sauce. You can also add across the rows and get the total number of people over 35 in the study, or less than or equal to 35. And notice that when I add the two numbers here or the two numbers here, I get the same result. Even though the two numbers that go into making it are different, I still get 79 as the overall total number of people that are in the study. So we can use this information in this table in order to find probabilities. And the first one we're going to look at is the probability that someone is over 35 or likes mild sauce. So over 35 would be here, or likes mild sauce would be here. And notice that that 22 actually got circled twice. So that's that, in this case, that would be representing the fact that they're not mutually exclusive. The likes mild or over 35, there's some people that are both. They are over 35 and they like mild. So not mutually exclusive. But in the table, we don't have to worry necessarily about subtracting as long as I don't count that 22 twice. So what I'm going to do here is say, okay, well, the probability of being over 35 or mild is going to be equal to, you just add all the numbers that satisfy either over 35 or likes mild without double counting the overlap. So I'm just going to have, let's see, I'll do 22 plus 17 and then plus 12. Those three numbers I circled basically. And then the total in this scenario, the total in the table is 79. So I'm going to get 51 out of 79 as the probability. So with the OR, you want to think circle a row, circle a column, and add up all the numbers that you ended up circling without doubling any of them. Okay, so that's that example. Let's look at the part B example, where we're now going to look at over 35 and likes mild sauce. So it can't be either or like it was in part A. We want the probability of over 35 and likes mild sauce. So now I'm just looking for the intersection. So the one that's common, and here in this case that would be 22. There's only 22 that are both over 35 and liking mild. So there would be 22 people out of the total 79 that were surveyed in this case. And that would be your probability. So at the and, think just that intersection, the one number that satisfies both the row and column descriptors. Okay, so the next one here then, probably someone is 35 or younger or likes hot sauce. Okay, so probability that they're less than or equal to 35 or younger, or hot. Well, let's go up here to the table again. So less than 35 is okay, less than or equal to 35, okay. Or likes a hot sauce, so any of the hot sauce likers are okay. And then I want to just add together those three numbers that I circled. Again, you don't double count the overlap in the intersection. So this would just be 12 plus 17 plus 28, no particular order there, over 79, the total number of people in the survey. And this ends up being 57 out of 79 for the probability. And last but not least, the last example we're going to look at here, and I haven't said this section, but you should be taking a little time to try these before I go through them. It's going to help you. I recommend that you try that. So probably someone's over 35 and likes hot sauce. So with the and here in this two-way table, when we're over 35 and liking the hot sauce, we're looking for the people who satisfy both qualities. So over 35 and like hot sauce, there's just these 17 people that satisfy the hot sauce and over 35 column and row respectively. So 17 out of 79. I'll go ahead and write this down here first. So over 35 and liked hot sauce. There were 17 that satisfied both those qualities out of the 79 total. Okay, so that's about it for this section. If you do have questions about any of the material in there, please ask. I can't help you unless you ask, because I am not seeing you like I normally see people. So make sure you are asking questions about this, and I will be sure to help you. All right. Have a good day, or night, depending on when you're watching this.